All right, good afternoon, everyone. Thank you for joining us today. I'm Colleen. I am covering for Kylie today. And welcome to our Roadway Safety Institute seminar about safety in numbers, bicyclist activity, and safety. This is part of our Advanced Transportation Technology seminar series. All of our seminars are open to anyone interested, whether you're practitioner, graduate, undergraduate student, or faculty. And the full schedule of seminars is available on the table over there, as well as on our website at roadwaysafety.umn.edu. For those of you taking this as a course, Kylie will bring back a full stack of your graded papers next week. Please contact her or Max if you have any questions in the meantime. And a couple of housekeeping reminders for those of you here in the room. Please do sign in when you come in or when you leave so we know who's attended. We need you to sign in whether or not you're a student. And if you have questions during Q&A at the end, make sure that you speak into the mic so that the web audience can hear you. For those of you watching us online, please use the chat box in YouTube to, one, let us know that you're watching and how many people are watching from your location, and two, ask questions during Q&A and we'll read those out loud. We have to report our audience numbers to the USDOT, so signing in here or online is really helpful to help us get an accurate head count. And with that, I am going to turn it over to Stephanie Malinoff.
Thank you. Good afternoon, everybody. Professor Donath is traveling again this week. I don't know how many of you know, but he's actually in Australia for a conference and is gone for about a month. So you'll see a few of us stepping in last week, this week, and I think 2 more weeks coming up. Again, my name is Stephanie Malinoff. I'm the program director for the Roadway Safety Institute. So thanks everybody in the room for coming and everybody online for watching. We're excited to have you here for the 6th of our 11th seminar in this series of seminars. We have Brendan Murphy with us today, who's going to talk about safety in numbers, which is this phenomenon where any individual vulnerable user, like a pedestrian in this case, has a lower exposure to risk in theory when there's more people, more pedestrians using that system. So he's going to talk about that theory and what they've been working on over the last couple of years here at the university. Brendan is the lead data scientist in the Accessibility Observatory at the University of Minnesota. He is a former University of Minnesota student as well, and I'm proud to say one of the Roadway Safety Institute's former Student of the Year award winners. So help me in welcoming Brendan, and we will do questions at the end.
Thank you all for having me here. Special thanks to the Roadway Safety Institute for inviting me to come back to this series, as well as thank you to the Center for Transportation Studies for helping put together this series. As it was mentioned, my name is Brendan Murphy. I finished my master's degree in transportation engineering about a year ago, working with these types of studies. What I'm going to discuss today is basically the wrap-up of a 2-year project that we've been working on at the Accessibility Observatory in looking at assessing pedestrian and bicycle risk of getting hit by cars in the Minneapolis metropolitan area. Today's going to focus on phase 2, which is the 2nd year of the project, within which we focused on bicycles primarily. Unfortunately, it doesn't look like she's here, but I want to give a special thanks to our colleague at the Accessibility Observatory, Kristen Carlson. She's a master's student in the civil department, and she did a lot of the statistical work and mapping and so forth associated with this study. So this is a brief outline of what we're going to cover. I don't expect it will take the full hour, so we'll hopefully have some time for questions afterward. I'll give a brief discussion of the background and motivation as to why we're looking at this type of phenomenon. I'll review our data sources and methodology, kind of how we're putting together the models that we're working with. I'll discuss our statistical results and some implications of those for practitioners and engineers. And then we'll open up the floor for questions after that. So we need to start with some definitions. Safety in numbers, if you haven't heard of it before, is a special phenomenon that shows that in an area, so in an intersection or an area of town where there's more pedestrians walking or where there's more bicyclists traveling along a section of roadway, we see a lower per pedestrian or per bicyclist rate of accidents with cars. Now, that rate is in contrast to the gross number of accidents that occur, since you would expect that if you put more people on bikes or more pedestrians or more cars into a system, the overall number of accidents would go up because you have more opportunities for them to occur. But the probability of any given person getting hit statistically goes down, correlated with the increase in activity in that area. So we in traffic safety research are trying to better understand why this occurs. We don't understand the causality of it, whether do more people walking cause a lower risk, or are more people walking because there is a lower risk? We don't really understand that. So this is a kind of a rough idea and a rough study to get at statistically on a citywide scale, how can we understand this phenomenon and what's causing it? So we want to understand how these risk values vary throughout a downtown area. Are there areas that are characteristically different than others, and what can we understand and glean from how those intersections are variably set up? Number two, we want to determine how the safety in numbers effect, or how the per user accident rate, depends upon the number of people biking or walking in areas. And then thirdly, we also look at what's called the safety and congestion effect. Now, congestion, you might think, refers to cars, and that's exactly correct. We assess the hypothesis that there might be a safety and congestion effect for automobiles, meaning the more cars that are present within a specific area, the per car accident rate might also decrease, similar to how the safety in numbers effect works for non-motorized users. So here are some data sources we had to go out and get from various electronic sources. We worked with US Census data to get us the geometry and the shape files and so forth that are required for this kind of spatial work. We use OpenStreetMap centerline data to help us get a data set of where the intersections within Minneapolis are located. We use what's called turning movement counts, which are manual counts, sometimes automated, but usually manual, of users moving through an intersection, and it's called TMC because they break out who's turning in which direction. And we use that to count up the number of users in an intersection. We also use a data source from Stephen Hankey and Greg Lindsay here at the University of Minnesota Humphrey Institute. They performed a study across several years using some data to estimate the bike and walk rate at a number of different intersections and street segments in Minneapolis. So that's an important input into our system. We also look at annual daily traffic levels for automobiles, since we need to know how many cars are going through intersections that we're looking at, as well as traffic crash records. And those are essentially the three very important data sets we're working with: counts of bike and walk, counts of car traffic, and counts of traffic record or crash records. So on the right side here, we have our process of taking that input data and starting to build models to understand this phenomenon. We first, as you usually would do, perform an ordinary least squares regression, which is the simplest, or one of the simplest ways of looking at statistical data for correlations. And we're looking at the rate of crashes and how it depends on the car traffic level and the non-motorized traffic level. And then we see across the population of intersections, how do intersections that are characterized by higher crash numbers behave with respect to their respective traffic counts, and how do intersections with very few or no crashes behave with respect to their traffic counts. Number two, we formed a different type of model, which is called a two-step model. And in this case, we used a first step of a probit, and the second step was a Poisson. To explain a bit, the first step of probit is looking at the probability of any given intersection having either no crashes or some number of crashes greater than 0. Since in this population of intersections, as you might find in any city, the preponderance of intersections, majority of them, have 0 crashes over some kind of time period that you're looking at, since crashes are, relatively speaking, few and far between, given the tens of thousands of vehicles we have traversing our streets on a daily basis. So we need to account for that large number of zeros we have in our data set, and it kind of treats it as a separate case. It's a little bit different to have 0 versus some number of crashes that occur. So that's the first step, is to group intersections into 0 and non-zero crash counts, and that's what the first step will do for us. The second step assumes that the intersections that have at least one crash occurring at them, the crashes occur as a Poisson process, meaning they occur independently of each other in a memoryless process, and we're able to model the number of crashes as a decreasing rate described by the Poisson distribution. And we compare those two to look at what proportion of crashes can we explain based upon the input variables of the car count and the biker walk count. Number 3, we assess and validate these models on intersections which we didn't include in the analysis. We use a standard 80% of training and 20% test statistical breakdown of the intersections used in the study. And finally, number 4, we use this data to inference the estimated bicycle risk burden and what's called the elasticity by input variable. And we'll get to look at tables outlining all of those in a few minutes. So just a visualization of the model methodology we used, kind of help you understand it. The first part is on the top. We have 2 different populations that are kind of fundamentally distinct of intersections based upon crash count. On the left, we have the population where we have no crashes, and on the right, we have crashes where there's at least one at that population of intersections. And then leading down into the second part, assuming that there is at least one crash, we can model the number of crashes as a Poisson process to use our input data set to model the number of crashes. And what this does is it allows us to build a statistical model of the number of crashes based upon the input variables without having our population of intersections muddied by the intersections where there's essentially no data, which means in our case where there's 0 crashes and 0 events that we're interested in. But it allows for us to account for the existence of zeros without throwing them out. And throwing them out would be not a good idea because you're eliminating proper data. So this is a visualization of the count locations for bicycle traffic. This is coming from a paper, I think it's due to be presented in next year's TRB, by Stephen Hankey at the University of Virginia Tech and Greg Lindsay here at the University of Minnesota. And it was, they constructed a model to estimate bike traffic throughout the city. So we're able to use their data as a pretty robust input of bike traffic throughout the city. And we're really, really thankful that this data set was made available to us. We use estimated daily bike traffic. This is a visualization of what came out of that model from their paper. They were able to use what's called a reduced form core model using these variables here to estimate bike traffic. The first one on the top, economic accessibility, is a variable that we at the Accessibility Observatory here at the University of Minnesota, that's the data that we actually provided to this study. Since the other studies and projects that we work on at the observatory look at this thing, which is called economic accessibility or accessibility to jobs, in terms of evaluating transit systems, in terms of how many jobs you can get to at the census block level. So we provided that data set to them. Then they provided the estimated bike traffic model to us for use in the study. They also built their model on other inputs such as land use patterns, weather factors, and other variables relevant to bike traffic and route choice making in bike users. And a rough idea of the range of estimated bike traffic levels was from 0 to 4,000 average users per day. The third input we have is the AADT, average annual daily traffic for cars. This is just a little picture of the AADT levels in downtown Minneapolis, of just the downtown core. We have the data for the rest of the city, but this is just a nice little view of the downtown core itself. This comes from a data set which I obtained from the city of Minneapolis between the years of 2000 and 2013. And rough range for this data set is 0 to 30,000. And what you're seeing here on the left, the bigger and brighter the little dot at the intersection means the more traffic at that intersection from these counts. And lastly, to tie those together at the event level that we're looking at, that we're interested in, is crash counts. These are counts from the same year set that the AADT is from. I got this data set also from the same folks at the city of Minneapolis. We're looking specifically at auto bike accidents. And of course, these have to be accidents that are severe enough to have been reported. So as we'll discuss later in our discussion of limitations and caveats, severity plays an important role in determining whether or not it's included in the study. Most intersections have 0 crashes reported. Doesn't mean that 0 occurred, it just means that based upon our data, we have to take that at face value, that no accidents occurred for our study. And not many have more than 10 auto bike accidents within this time period. So that means that on an annual average, most intersections even have 0, since these are pretty uncommon events that occur, which creates some statistical difficulties when dealing with these low event rates. This is a brief description of the input data sets that are feeding into our models. Just giving you a quick look at the minimum, maximum, and average values for this. We have on the top the crash count. We have vehicle traffic for cars. We have bike traffic closer to the bottom. And then these squared terms, which are actually pretty important to discuss. We include the square of both auto traffic and the square of bike traffic in our models. And that doesn't directly correspond to a specific count of people moving through an intersection. But what it does for us is it lets us include a variable in our model that speaks to the situation of, well, what happened if we dumped a bunch of cars into an intersection, or if we had tens of thousands of people biking through a segment of roadway. And it lets us assess what an extreme case like that would be and what that case would do towards our assessment of crash rates. So if we saw, a huge increase in car traffic or a huge increase in people walking, say over a 10-year period, we built a new WUNERF, like we did here with the University of Minnesota Transitway, or we built new facilities that tenfold increased the number of people willing to walk in an area, what effect would that have on the crash rate? So that gives us a second-tier variable to include in our models. The first order of business for our modeling was to look at an ordinary least squares regression. And that is, again, one of the most basic first-line statistical shots you take at looking at a data set to look for correlations. We looked at, again, vehicle traffic and bike traffic as explanatory variables for the number of crashes that occurred. And what we see is lines 1 and 3 for the vehicle traffic and bike traffic. Both coefficients are positive and significant at the 90% level, so that's good. That means that increasing the traffic levels at an intersection corresponds to an increase in the gross number of accidents that occur. That makes sense. We would expect that the number of accidents is positively correlated with the number of people moving through a space. So good. The square terms here are negative, as we also would expect, because if you saturate a system well beyond the carrying capacity of cars or bikes or pedestrians, then the system kind of locks up. And then you're operating in a very different regime, a congested regime, and you would expect that the number of accidents would eventually start to go down as people couldn't really move through anyhow. But using OLS, we're only able to explain 10% of accidents that occur. So maybe the two-step model might do a little bit better because it accounts for the fact that we have a preponderance of zero of intersections with zero crashes. And that is indeed the case. Again, we found positive and significant coefficients for the vehicle traffic for cars and the bicycle traffic for bikes for those variable inputs. So that's good. It agrees with the OLS regression, which we just saw. And then we also have negative values for the coefficients for the squared terms for cars and bicycles. So this model does agree with the influence of car traffic and bike traffic on the number of crashes that occur, which is good. And additionally, our R squared is conveniently a little bit higher. It's actually 0.35 instead of 0.1. Right here, for the OLS, we have an additional 25% of explanatory power, basically. We can explain 25% more of the crash counts at intersections by using a two-step probit Poisson process over using a simple OLS regression process, because it accounts for the high number of zeros that occurred in the crash count population. So we now need to evaluate. We know the relatively low explanatory power of 10%, 0.1, and 0.25 additional, so 0.35 total for the OLS and the probit Poisson models. Did they do well in terms of overestimation or underestimation, or were they right in the middle with dispersion of estimates on both sides equally? So let's look at the OLS regression first. We have on the bottom, that's the observed crash count at our intersections across the whole population of them. And on the left, we have the estimated crashes based upon our models. And then this line is basically the line of identity. If an intersection lies along that line, that means that our model predicted a number of intersections in agreement with the number of crashes at that intersection, in agreement with a number of crashes that actually occurred, at least in the data. And if it lies to the right of this line, that means that we underestimated. To the left, we overestimated. And as we can see, the ordinary least squares regression model at intersections where there were a lot of crashes underestimated the number of crashes, and at intersections where a lower number of crashes occurred, we overestimated the number of crashes. How does that compare to the probit Poisson process? This model does a little bit better, but again, we see that at intersections characterized by a higher number of gross crashes, we underestimated the number of crashes that would occur based upon our predictions. And also, same thing, intersections with a lower crash count, we overestimated the number of crashes that would occur based upon only the two inputs of car traffic and bike traffic. And there are a lot of other variables we could include and have been included in other studies, and I'll discuss what those variables add and mean in a few minutes. We also looked at elasticities of the four variables that were included. And what this gets at is if you change bike traffic or if you change car traffic by a set amount, say 1%, what is the corresponding marginal increase or decrease in the number of crashes that occur? And if the elasticity is above 1, it's said that this variable has an elastic influence on the number of crashes. And if your elasticity is lower than 1, then it's said to have an inelastic influence in the number of crashes that occur. So based upon the ordinary least squares regression, we see that vehicle traffic has an elastic positive influence on the number of crashes that occur, and that the flooding of the system with car traffic, the square term of AADT, has a negative influence and inelastic influence on the number of crashes that occur, as would be expected. The bike traffic has an inelastic influence, but positive, on the number of crashes that occur. And what that tells us is that the marginal change in risk due to an increase in bike traffic or bike count is lower than the marginal increase for car traffic, which tells us that cars are riskier than bicycles at a given intersection. And same with the vehicle traffic. If we square the term of bicycle counts, we see a negative inelastic influence on the number of crashes that occur. Compare that to the two-part model. The probit model, again, gets at assessing whether an intersection has 0 or more than 0 crashes. We see a positive inelastic influence of vehicle traffic on whether an intersection has 0 or more. Now, positive here indicates that an intersection is more likely to be in the population that has greater than 0 crashes versus the population that has 0, since the model determines between 0 or 1, basically. Same with the vehicle traffic squared term. We have an inelastic negative influence. And then the bike traffic and the bike traffic squared also agree with the assessment of the OLS regression. In the part 2, again, we're looking at modeling the number of crashes that occurred at intersections given that at least one occurred. And these agree also with the OLS, except for the one difference here is that the OLS model gave an elastic influence to auto traffic, whereas the two-part model said that the influence of vehicle traffic on number of crashes that occurred was inelastic. So what does this all mean? This means that traffic levels, in general, can only explain a small portion of crashes. If you'll recall that the R squared of the OLS model was only 0.1, and the pseudo R squared of the two-step probit Poisson process was only 0.35. Those aren't very good, but they make sense given the context. There are a lot of other factors that go into the occurrence of crashes at intersections, such as things like intersection geometry and the speed of the roadway, the capacity of the roadway, environmental factors such as the number of trees, if there's cool things to look at for people to get distracted when they're driving, and so forth. Crashes are a stochastic process, which means that it's really difficult to predict the presence of one crash or no crashes, since especially at that low occurrence level, it's basically random. It's kind of a crapshoot whether you get a crash happening at, say, the intersection of Washington and Huron or not. And there's no continuum for this type of event. There technically is in terms of, say, the distance between two bumpers on two cars, but that's not a quantity that we really look at or that we measure. It's either two cars hit each other, or a car hit a bicyclist, or a car hit a pedestrian, or it didn't happen. And those negative events, we don't really record. You can get at that statistically, but it's a difficult thing to basically shunt into models that are used to dealing with continuous processes. So tying it back to our hypotheses, which were that, number one, we would see a safety in numbers effect for bicycles, and we would see a safety and congestion effect for cars. We did find evidence of these phenomenon in the data sets for Minneapolis. And they also, our models also reflect the influence of saturation or operating an intersection at a congested regime versus a free flow regime in terms of the number of accidents that can occur. We found that the two-step Probit-Poisson models predict 25% more crash counts accurately than the ordinary least squares regression model does. And we hypothesize that this is due to accounting for the zero inflation of the population of intersections, since most of them have zero crashes, or the data set is essentially skewed towards zero. Accounting for that in a two-step model allows us to look at the populations essentially as distinct. Both models underpredict high crash intersections and overpredict low crash intersections. And we hypothesize that this is due to not including other factors that could be included and that might help us explain more of the tendency of crashes to occur. And here's some examples of those things. If we look at factors such as car traffic by street length, that might help in explaining how crashes occur. Since around this area, a lot of the roads are of similar or exact same type. If you go into Dinkytown, the roads don't have that much different traffic levels. The speed limits are all the same, and it's pretty homogeneous throughout the space of intersections and roadways in terms of how the road is set up. However, if you have an intersection between a trunk or a primary roadway and a very small feeder street that have drastically different AADT counts, that's a very different situation than if we look at an intersection, say, at Como Avenue and 18th Southeast in Como. And that is a very distinct situation because we have a primary artery that's being crossed by a much, much smaller street, and a bicycle or a pedestrian on that smaller street crossing this big, scary road is going to have a different experience on the roadway than they would crossing an equivalent roadway. So those situations would be important to split out from the other population of intersections. We can look at signalization, which is the presence of an electronic powered signal at the intersection, since that gives us a totally different regulation of traffic compared to a stop sign regulated intersection or a two-way stop or an ungoverned intersection. We can look at intersection geometry, which is the number of lanes that approach an intersection, since that allows us to look at the presence of things like protected left turns, right turns, whether right turn on red is permitted, which in Minnesota it is, as well as the number of intersections influencing the presence of blind spots, which leads to things like right hooks for bike users, which is a big risk. The presence of bicycle facilities is also potentially a very salient variable to include in these models, since a common school of thought right now in assessing bicycle traffic levels is to look at what's called the stress level. A higher car traffic roadway is going to have a higher stress level. You can think of it as, I'm very stressed and I'm anxious to bike on this roadway. That's a good way of kind of materializing it for yourself. And smaller roadways with less traffic and more residential areas with smaller street widths are going to have a lower stress level. Or if there's a protected bike lane, or if there's a buffered bike lane, those are going to be lower stress pathways for bicycles to use. And the presence of bicycle facilities, number one, influences the bicycle traffic on the roadway, and number two, could have some kind of influence in the rate of accidents that occur. And finally, if we look at approach elevation changes, that kind of ties back into the intersection geometry bit. If you have to decelerate because you're going down a hill approaching an intersection, some bicyclists might not be so inclined to brake as hard. They might be more inclined to run the red lights. Or if you're on an upswing towards an intersection, cars might have a blind spot at a 90-degree approach to be unable to see bicyclists coming from the other direction. We don't have a whole lot of that here because Minnesota's pretty flat, but it might be relevant for some place like San Francisco and California. So at this point, I think we can start opening the floor for questions, if anyone has any to offer.
Great. Thank you. Anybody in the room have questions? If you're watching online, type questions into the chat box, and we will read them aloud for Brendan. Any questions here in the room? All right. Just 1 second. I'm going to bring the microphone back.
Well, thank you so much for your presentation. Towards the beginning, you said something about using the 80-20 rule for intersections, and I wasn't quite sure what that meant. If you could talk about that.
Sure, yeah. So the 80-20 is a reference to when you're kind of training a statistical model to take 80% of the population of things that you're looking at. In this case, it was about 400 intersections where we had crash data and we had count data. Take 80% of those and build our model on that 80%, and then test our model by seeing how well we predict the number of crashes at the remaining 20% based on the inputs at that remaining 20%. And that lets us statistically separate out the population that we're training on versus the population that we're testing on, so we're not just patting ourselves on the back and saying, oh, great, we built a model on this population and it predicts the crash rate at this population really well. When you include the population in both of those steps, you don't get a good test as to whether your model is robust or not.
Great. Other questions? Anything online? Okay. Well, let's thank Brendan one more time. And 1 second. I had the piece of paper in my hand, and then I forgot it. Next week, we have a presentation by Professor Gabriel Xiaber from the Department of Aerospace Engineering and Mechanics here at the University of Minnesota. He's going to be talking about current and future GNSS applications for vehicle navigation and guidance. And if you're like me and had no idea what GNSS stands for, Global Navigation Satellite Systems. So stay tuned next Thursday. We'll be here, same room, same time, online as well. And thank you all for coming.